we're going to walk through how to do a semi-empirical model with moving horizon estimation. So when we talk about semi-empirical modeling, we're going to be combining elements of something like a first principles energy balance. Okay, so that might be our first one that we use, an energy balance from fundamentals, conservation of energy. But then there might be elements of this model as well that we're going to use an empirical or black box correlation. So this is our last estimation lab that we're going to use with this temperature control lab for the dynamic optimization course, and we're going to be designing this moving horizon estimator. I have a suggested form of the model, but if you would like to use other elements, you're welcome to. So up to this point, we've done a pure energy balance form, and we've also done a purely empirical form, and we're going to be combining these two now, and we call that a hybrid or a semi-empirical approach to modeling. Okay, so we have our setup here with our two temperature sensors and our two heaters. And the two heaters are the actuators. The sensors are going to be recording the data. And we want to collect data over a 10-minute data collection period. Now, in moving horizon estimation, we might be going for days or months or years. And we always maintain a moving window. Okay, so if you think of this as like a window, we maintain a moving window of data. And then as new data is added, we simply shift the window over and add the new data point. And this one would fall out of that moving horizon window. Okay, we also want to include a couple things like asynchronous staggered steps of the heaters with varying magnitude and direction. That's going to be important in order to be able to help us estimate. We need to have basically perturbations to the inputs to be able to get the dynamic relationships. Okay, so here's some starting values for the energy balance model if you didn't get those already from Lab C. Okay, so it's preferred to go back to Lab C, maybe get the best parameters that you identified from the energy balance just to start this one. Okay, so we have 3 parameters from our energy balance and 1 parameter, and this is going to be from our empirical correlation. Okay, now you can do other forms as well, but this is just the suggested one. We have here the energy balance equation. Now this includes convection, radiation to the ambient conditions, convection to heater 2, and radiative heat transfer to heater 2, and then our energy input term. And then similar for the second heater, we have convective heat transfer, radiative heat transfer, convection to heater 1, radiation to heat 1, and then also the input source term there. Okay, and then we have 2 empirical correlations as well, and this just relates the temperature of our heater to the temperature of our sensor. Okay, so here's our sensor, and here is our heater right here, and we just use a simple lag equation. Now there's just one parameter there, tau. So let's say the temperature of the heater all of a sudden does this. This lag equation essentially just says I'm going to come and eventually get there, but there's going to be a little bit of a lag that's characterized by this tau value, and that tau value is how much time it takes to get a little bit over halfway to the new temperature. So we know that there is going to be a little bit of a lag. Okay, so this is our temperature in degrees Celsius. That's our sensor, and if our temperature of our heater changes very quickly, this equation right here will approximate the little bit of lag or time delay that occurs between the heater and the sensor. Okay, so there's going to be some questions there, a little bit of help on tuning as well. And just in terms of some of the tuning parameters that you might adjust. Okay, so they're listed there, and then there's also a good starting point if you're intimidated by starting from scratch, from nothing. You can use this. There's going to be a starting point in Gecko. There's also one in Matlab as well. So let me just show that to you. So what we'll do is we'll just go to the just come to the let's see, the website for the lab, and that's just going to be APMonitor.com/heat.htm. And then if you scroll down, you'll see some of the lab solution files in GitHub. And the ones that we're going to be working with here are going to be number 5, moving horizon estimation. And in here we see second order nonlinear. That's the one we're going to be using for this lab. Okay, and so if you come down, you'll see a Matlab and a Python Gecko. And what I'll do first of all is just go ahead and run the Python Gecko one, just as we're talking about the code and what it's doing, just so you can see an example here of it running. So I have my temperature control app plugged in. I'm just going to run this. Okay, it's going to connect. And also, if I'll just show you one thing here. If you have a local server, you can use, okay, I'll just show this to you off to the side. Okay, this is a real-time plot, so it sometimes kind of takes over your, looks like it's kind of taking over your computer screen. Okay, so also if you have a local server, you can basically uncomment this, and that will let you run locally, or you can do a remote equals false when you solve it. Okay, both of those should work. Okay, so I'm just going to step through some of the code here just as we're letting this run, and then we'll just see some of the results of this. Okay, so I'm going to scroll down. I've kind of annotated the code here just with some pseudocode just to help us see the structure of the code and what's going on with this. Okay, so you can see, looks like my Arduino lab froze up a little bit. It was kind of not responding there. Let me go ahead and just kill this one. I'll close the program. I think it didn't like it that I was moving the plot around when it was trying to run. Okay, so I'm just going to run this again. Okay, and you know what? Okay, I'm just gonna, I'll run this one more time. And we'll just see if we can get some results. It already heated up one of the sensors a little bit, and we'll just see if this is able to run. It's already at 40 degrees, so there's going to be quite a bit of mismatch initially, and then you'll see it kind of catch up after a little bit. Okay, so you're going to see, every 3 seconds it's going to update it with a new measurement, and then you're going to see, the heater turn on, for example, right there after a few cycles, and then you're going to see it try to start aligning by adjusting the parameters. So we're not adjusting any of the parameters yet. We're going to wait a few cycles. Okay, now you can see the parameters start to adjust. The parameters are listed there in the second subplot, and there you can see it trying to start to match up to the data. Okay, so we'll let this run. We should also be able to see, for example, it'll open up a web interface for us. Okay, and we'll see that after a little while when it opens up. The web interface will be able to see a little bit more about what the measured and estimated temperatures are doing. Okay, so you can see now the second heater just turned on, and you can see that it's matching up, starting to match up just a little bit better on the first temperature, there's a large dynamic mismatch initially. Okay, you can see the heat transfer coefficient, that empirical time constant, and then the alpha values that are adjusting there as it's aligning to the measured values. Okay, so now I'm going to try to move this off to the side again. Okay, it didn't work so well the first time, but we'll try this again. And okay, and just go through some of the pseudocode here. It's going to be, okay, there we go. Okay, so what we're doing with this is we first of all just import some packages. We need Gecko, we need TCLab. Both of those are pip installable in Python. And then we'll connect to the Arduino lab. Okay, and then the next thing that we're going to do is just specify our final time. We want to go for 10 minutes, and we're going to go every 3 seconds we're going to update the moving horizon estimator. Okay, the next thing that we're going to do is just give us our heater values. Now we also want some random values, so at cycle 50 you can change this of where you want it. I think in a later script I changed this to a later point that every 10 samples we're just going to select a random heater value right there, and do that in staggered every 5 cycles. It'll be either Q1 or Q2 that changes. Okay, so that just gives us our inputs. Okay, this is just recording some values for plotting. We want to record, the temperatures. We want to record the moving horizon estimation, temperatures as well, and then the 4 parameter values that we're trying to estimate. Okay, we're going to initialize the estimator right here. That's just our model, our Gecko model. Okay, we're defining the time points. We're only going to go back 20 steps on this. And then the rest of this is just setting up the moving horizon estimator, some of the parameters. So we have our heat transfer coefficient U, we have our tau value, that's the empirical parameter, and with each of these we see that we initially turn the status off. We turn its F status off as well. We're not measuring anything, so the feedback status is off. And then we set some constraints as well. The Dmax is going to be the delta maximum, how much that parameter can move each cycle. We have a lower and upper limit as well. So just give some physical realism or some bounds to those parameters. Now you can see that with the tau we're doing the same thing. The alpha 1 and the alpha 2, those are 2 more of our parameters. Those are the heater effectiveness. Okay, and so you can see it's going to be estimating those 4 parameters right there. These are measured inputs right here, Q1 and Q2, and we're going to declare those as MVs because they're parameters. They're going to get a measurement, and then let's say this is our Q value right here. It's going to get a new measurement. Let's say it got a new measurement right here, and then that measurement is going to fall off of the horizon. Okay, so that was our initial window right here, and then it's going to advance 1 forward, and that's going to keep track of that changing input. Now we measure it, so our F status is 1. That's our feedback status, but we're not trying to optimize the Q1. We'll turn that one on for the controller, and that'll be later. Okay, we have our state variables. These are the 2 energy balance variables. Those are the temperatures of our heaters. And these are the ones that we're actually measuring, the TC1 and the TC2. And you can see that in the top subplot there, how we are measuring and trying to align those. Now, we have, the status and F status are on. Okay, so we're telling it to include that in the objective function. And then we just gave it a lower and upper bound. We don't necessarily need to do that, but it just gives the solver a couple bounds so it doesn't try to find temperature values that are outside that range. Okay, and then we have some parameters these are just fixed values that we're not really ever going to change, or estimate. Okay, and then we get down into the equations. We have a couple intermediate variables. These are kind of like temporary variables that are defined just to simplify the the expressions down below. So for example, QC12 is used here and is used here. So this is just going to substitute that value in those expressions. Okay, so it's going to calculate it and substitute it in. Okay, but we have our energy balance equations. This is our first principles approach right here. And then we also have some empirical correlations. So we're combining those two together. Okay, next we have some options right here. This just tells us to go into moving horizon estimation mode. We have a squared error objective, and this is a number of collocation nodes. We use the IPOP solver, and we're also going to cold start just on the first cycle, just to help us initialize 0 degrees of freedom. Okay, the rest of this is just plotting and running the moving horizon estimator. We have our plot, okay, and we go through this, sleeping for a maximum of 3 seconds. That's just controlling some of the time. Here's where we actually read the measurements in Celsius, and then we insert the measurements into our model. Okay, here is where we're going to turn on the parameter values, the status values. So we say after cycle 10, then we're going to start recording those values. Here's where we actually solve the moving horizon estimator right there, and then we just retrieve the solution and put it into some of these variables so that we can plot it later. Okay, we're going to also write the new heater values to the device for the next cycle and then wait 3 seconds. And then this is just plotting. This is just creating the plot that you see right over here. Okay, and then this is just turning off the device, shutting down the heaters. Once we're done, we can look for a Control-C event on the keyboard, or if the serial connection fails, or just if we finish that loop. Then it's going to save the figure and it'll shut down the heaters. Okay, so that's it for this one. You can see this continue to go. We're into the region now here, starting at about 380 or so, where we have more of these random variations in the heater values, and it actually is better. It'll actually stabilize some of our parameter values a little bit more because we have more dynamic data, more excitation of the inputs, and so we're going to see potentially better estimates of our of our parameters in that region. Okay, so we'll just let this one finish. I just want to show the Matlab one as well. I just kind of have the equivalent Matlab code over here too. Okay, I'll just go ahead and bring this up just as the Python one is finishing, and we'll just start the Matlab run just to show you kind of the equivalent of what's happening with Matlab. Okay, so okay, this one is almost done. Let's just see if it's finished. Each cycle, it looks like it's taken about 0.1 to 0.2 seconds. Okay, it looks like it's done now. Okay, I'm going to go ahead and close this one. Okay, you can do some things to tune the estimator a little bit better. Okay, I'm going to open up the Matlab version now, and just open up the main MHE, and I'll just start. I'm going to plug in my other Arduino device that already has the Matlab drivers located, or if you just left the Python one there, you could run it and it would automatically load the the Matlab drivers on it for you. Okay, and if you do that, you just have to load the Python firmware back to convert it back to a Python version of the lab. I'm going to go ahead and run this. You're going to see a very similar thing, just a little bit different. though, and I'll expand this just a little bit more as we're talking about the Matlab. Okay, so very similar to Matlab. We're just going to load the APMonitor toolbox. You just need to get that folder. It's also available from the download that I showed. We're going to specify our server. Again, if you have a local server, that's freely available. Just specify the server address as such, or you can do localhost. Okay, and then we're going to connect to the Arduino. We'll say runtime. Here's our number of loops. And then we're going to, like we did for the other one, we're just going to specify the Q values that we want. Okay, those are our header values. We're going to store some values for the plots. And then here's where we call, I just put that in a subroutine, a function. There's where we initialize the moving horizon estimator. So let's go find that. Okay, and we have right here the MHE init. And this is going to load our model file and load a data file as well. So that's where we have our equations and the horizon, the time points for the moving horizon estimator are stored right there. We're going to configure our parameters, our state variables, our controlled variables. Okay, here's where we tune our different parameters, Dmax, lower, and upper. I'm going to have initially the status off, so I'm not going to try to estimate those. And then also the F status has to be off so that I don't try to, I don't have measurements for those. Okay, but I do have measurements for Q1 and Q2 as we talked about. We're going to use TC1 and TC2. Those are going to be our two measured temperatures. This just controls the web interface. That's the plot frequency, how frequently it updates. And then here's some more options: moving horizon estimation, squared error objective, 3 nodes per time step, IP-opt solver, and then cold start on the first step. Okay, so that's our initialization right there. I just want to show the model because we loaded the model right here. I just want to show you that model, and I just included it right here. So this is the APMonitor modeling language. We built that in the Python. It writes that model file for us. But in case you're using Matlab, you're going to need to potentially write this one yourself. Okay, so here are the constants in that model. Those are just values that are never really going to change. We don't want to update them. Here are our heater values. Here are the 4 parameters that we're going to try to estimate, and we've given them some initial values. We've given our 4 variables. We're going to have 4 differential equations, so we need 4 variables. Okay, and then we have some of our intermediates. Again, these are going to be plugged in down here. You can see where those are used. And then we have our energy balance equations. Okay, and this, the dollar sign is the differential. Okay, whereas in Gecko it's .dt, open and close parentheses. And then we have our empirical equations as well. So there's our, this one is our model right there. Okay, and I'll get back to our main script here. The next thing that we're going to do is just create some plots. We do that before the main loop starts, just to initialize those, and then we'll add the points to it. It'll make it a little bit more efficient if we're just adding 1 point at a time. Okay, and then down, this is the main loop right here within Matlab. We're going to loop for those, every 3 seconds for those 10 minutes, and we're going to adjust the power levels, and then we'll pause. This is, just recording some of the times. This is where we actually read the temperatures from the device. After 10 cycles, we'll turn the status on for those parameters, so start estimating them. And then we're going to solve the moving horizon estimator, right here. That's the line, and it's just going to return the parameter values, and then we'll add some points to the plots. Okay, after 20 cycles, we'll open up the web interface, and Looks like that one opened. I'm just going to select this plot right here, TC1, just to be able to see the, this will show the plot, the measured, and the model values. Okay. Okay, so that's the web interface. You can also change parameters here if you want to. Okay, you can change, if you go to any of these, like let's say you go to CVs tab, you can change things like, let's say you forgot to change something like measurement gap or something like that. You can change that right here from the web interface. Okay, so that's the web interface if you want to change things on the fly. Okay, let me get back to just one thing that I didn't show, which was this function right here, the moving horizon estimator. Let me see if I can bring that up. There it is right there. So it's not very long, but this is basically what we're doing. We have the two temperatures that we're reading in, and also the two heater values, and then we're going to return some parameters and the measured temperatures. Okay, we have our input measurements. We insert those with APMez. We solve the, in this case it's an MHE, not an MPC. We test to see that it was successful. We check for the app status, the application status. If that's equal to 1, then we say it's good. And we're going to retrieve like the new value tags from the parameters and the model values from TC1 and TC2. Okay, so for MVs or FVs, we have to retrieve the .new val, and for SVs or CVs, we're going to retrieve the .model. Okay, this is if it's unsuccessful. Right there, I'll just load in some default values, and then we need to return our 6 values. The params are 4 estimated values, as well as our 2 that are predicted, which are 2 temperatures from the temperature control lab. Okay, so you can see now, let me just make this a little bit larger. You can see, the estimator working. It's trying to align to the model values there. You can see initially it was trying to figure that out, up until about cycle 80 or so, 80 seconds, that we had some large parameter value changes, and then it looks like it settled out just a little bit more. Again, during this time period of rapid changes, we're going to get hopefully more dynamic information into our model because we have more perturbations of the inputs, although those aren't quite as large or sustained. Okay, so I hope this helps in terms of understanding the code, what we're doing for the moving horizon estimator. In this case, the big thing with this is really combining elements of a first principles model as well as an empirical model, and trying to make those the best elements of both of those work together in a unified model. Now the next step for this assignment that we're going to take is really to take it one step further, and we'll do this after the midterm exam, and that's just going to be designing a controller for this. And the controller is going to be, let me just go to the course website. Okay, the dynamic optimization course website, and we've been working through a lot of these labs already. You can see on the right hand side the Arduino lab. We did started off with a single input single output model, a MIMO model, so just some of the modeling. The lab C was a batch parameter estimation, with the first principles model. We did lab D, which was our first kind of experience with moving horizon estimation, and this lab E is the hybrid model estimation. So now that we have good models, we're going to go to the next step, and that's going to be developing model predictive controllers. So those are going to be updated. Okay, so we might have, for example, these models that we're obtaining, the parameters that are being estimated, maybe in real time, and these are really looking backwards in time. And then we're going to take these models and help us look forward in time to be able to see how actions like on the heaters are going to be able to affect the temperature, reaching a certain desired temperature. So instead of us just giving the Q1 and Q2 values, we're going to let an optimizer plan out a move horizon on those. What are the heater values for the next 3 minutes or so, and we're going to use the model to help us predict what the heater is going to do. So this is the purpose of the estimator, is that then it helps us develop a model that's aligned to real-time data, and then we can use that model to help us develop a model predictive controller that's going to be able to help us predict into the future and use an optimizer to help us come up with these better values for the future. Okay, well that's it for today. I showed the Python and the Matlab versions of this lab. I hope you enjoy it. And again, if you want to get a copy of the lab, if you're kind of new to this, just come to the home page on this, and you can come down here. There's some information on buying or building a temperature control lab, and you can do that through the this link right here. Okay, we'll check back in next. The next video for this lab will be about the model predictive controllers.